So, what's the reaction that's really taking place here? Here's your acid, HNO2, weak acid, and it's not the sodium ion, we don't care about that, it's that hydroxide ion, which is a strong base. The hydroxide ion reacts with the weak acid, HNO2, and you have to be able to figure out what the products are going to be. Figure out the H plus transfer from the acid to the base, you end up with the nitrite ion and water. Okay? So let me go through this last part, part E, and kind of go through that sort of problem. And again, maybe, yeah, so let's just go through part E, so don't get too confusing here. So again, understand the chemistry going on here. Go to that camera. Zoom out a little bit. Okay, so what we have going on here, we're mixing this weak acid with the strong base. So the weak acid, HNO2, the strong base, you don't care about the sodium ion, just like in the previous slide, but you care about that hydroxide. So you have to understand what's taking place in the reaction. So in this case, you have the base of hydroxide, you have the weak acid, and then you have to figure out what are the products. Okay? So you have a strong base, weak acid, on the reactant side, so it's not equilibrium, it goes to completion, and you form the water and the nitrite ion. So it's going to be, notice I draw this as basically a one-directional arrow to emphasize that the reaction pretty much goes to completion. Okay? So when you have a reaction with stoichiometry, you work with the moles, and you figure out that, okay, oftentimes one will be a limiting reactant. Which one's going to be a limiting reactant? Well, the good thing for a lot of acid-base reactions, the stoichiometry is 1 to 1. Okay, so there are some, oftentimes, simplicity is associated with these acid-base reactions, one of which is oftentimes, not always, the stoichiometry is 1 to 1. So, to figure out which is the limiting reactant, you have to figure out the number of moles of each, and from that it'd be pretty straightforward to figure out which is the limiting reactant. So you figure out the moles, the way you always do. Take liters times molarity, gives moles, and you see that there's basically what? There's more than HNO2 than we do with hydroxide. So the reaction that takes place with the hydroxide reacts with HNO2. We have a limited amount of hydroxide, so all this hydroxide reacts away as a limiting reactant, and you're going to have HNO2 as the excess reactant. So what you want to figure out is how much of the conjugate base is formed and how much excess acid is left behind. So it's a limiting reactant problem, and we've done several of those before. So you kind of figure out. The question out there? Oh, I heard something. So basically, yeah, the excess. What's about the excess weak acid? You take the difference of the two. After you react away 0.00075 moles of the HNO2, how much is left? Well, 0.00175 moles. That's the excess weak acid. How much of this conjugate base is formed? Well, every hydroxide reacted to form one NO2 minus. So whatever moles of hydroxide reacted is going to be the number of nitrite ions that formed. So if you had 0.00075 moles of hydroxide, you're going to have 0.00075 moles of the nitrite ion. Okay? Now, you did the stoichiometry. Okay? You recognize the limiting reactant. You figured out what you have after that reaction. Now, unfortunately, you're not quite done now. Now you ended up with a solution with a weak acid and a conjugate base. So now there's like a second part to this problem. And the second part of the problem is, since this is a buffer solution, a weak acid and a conjugate base, we now have to work out an equilibrium which takes place with the initial concentrations of 0.12 molar of the weak acid, HNO2, and 0.05 molar of the conjugate base and O2 minus. Okay? Questions on that so far?
So those are the,
Go ahead.
so those are the equilibrium concentrations, the 0.12 and the 0.05.
The 0.12, the 0.05?
Those are the equilibrium concentrations.
Yes.
Okay.
So here we have the number of moles, and then I set up to do a Ka calculation, and you would have that basically there. Okay? Yeah. So at that point, two ways in which you can do this problem. So the second step now is when you have the weak acid and conjugate base, is to work out the what you have at equilibrium with these two species in solution. And the quick way of doing that, since you already did a lot of stoichiometry, you're looking for shortcuts, and since you recognize you have a weak acid and conjugate base, it's a special case where we have buffer solutions. We can use what we call the Henderson-Hirschbach equation. I showed this before. Where pH equals pKa plus log of conjugate base over the weak acid. Now this ratio here, again, could be in moles or could be in molarity. It doesn't matter because whatever volume you have for the solution, it's the same for the conjugate base as well as the weak acid. So they would cancel out as a ratio anyway. Why do I emphasize the point of this ratio to be moles and molarity? Well, if you look back at what we did just prior to that calculation, we did stoichiometry, right? And that stoichiometry with moles, we did basically, we have the number of moles right here. So we could have used just these moles here to figure out what the pH of that solution would be. Okay? The other one, okay, so in this case, actually, I took it in terms of, I did it. So actually, I did do it in terms of molarity. At first, I was going to use the ice table and use these concentrations, but since I used this Henderson-Hirschbach equation, there's a ratio, that's all I need is the ratio of the two. So moles and molarity, I use either one here, and I use moles here, just for the sake of that calculation. And you do the calculation, and you have pKa of 4.6 times 10 minus 4 for Ka would be 3.34. And that long-term ratio is minus 0.38. Okay? And the fact that we have basically more acid than base, the denominator is bigger than the numerator, that long-term is going to be negative. And that kind of makes sense, because if the solution of a mixture of weak acid and conjugate base is such that you have a little bit more weak acid than conjugate base, it's going to basically have an effect of lowering the pH a little bit, making it a little bit more acidic. Okay? So the actual number is minus 0.38 for that long term, and the pH of the solution is 2.96. Now, the other way of doing the problem, you could always go back to the ice table as well and solve it that way. Okay? So the ice table way, if you do I won't go through the whole thing, but how would you do the ice table? Well, I would just write the Ka expression, the equilibrium reaction, I should say. Okay? And the initial concentrations, but here you do have to use concentrations. You should have, this is 0.12. This was 0.12 molar. This was 0.05 molar. And just, use your minus x plus x plus x as you've done before. And then you have Ka equals what? X times 0.50 plus x over 0.12 minus x equals your Ka, 4.6 times 10 minus 4. Okay? Now, I'll show that a little bit. So again, rather than do the Henderson-Eschenbach equation, it could be done